We have been discussing last week on membrane preparation. And now we are going back to discuss some very important aspects on any membrane operation. Until now, we have been presenting some advantages, some positive part of membrane engineering. We have to consider some drawbacks, some problems. And one of the major problems we have in all membrane operation, reverse osmosis, ultrafiltration, electrodialysis, is what is called membrane fouling. This is an intrinsic aspect of any operation. So it's something creating damage, but it's something that you have to expect. If anybody is trying to tell you that you can make a nice operation with membranes with no fouling, don't trust. Fouling is also present, and you have to learn how to handle and how to solve the problems. If you assume there is no problems, that can be dangerous, because the problem will appear. So we have to consider this is what we call intrinsic aspect of any membrane operation. And basically, the origin of the fouling is the fact that during the separation, extraction of water from seawater, or treatment of any kind of aqueous or non-aqueous solution, you can have phenomena in which you can have adsorption or deposition of some material which are present in the feed solution that you are treating on the membrane surface. It can be just adsorption or just deposition, and that is giving some problem. You are increasing, for example, the thickness of the membranes, so you are increasing resistance to the mass transfer. You can change the behaviors of your membranes. The membranes can have some ion exchange effect. With some adsorption, you can neutralize the ion exchange effect. So you change the chemical behavior, etc. Normally, this kind of phenomena, adsorption, formation of a thin layer, chemical transformation for a pH variation, for example, will induce change in transmembrane flux, reduction of the permeate flux, and also, in general, you can change the solute transmission. That means selectivity. The selectivity system can change. So an important phenomena. That is when you are working with a constant transmembrane pressure normally. If you are working your system with a constant JV, that means volume of filtrate, you can have a significant increasing in the transmembrane pressure. That means pressure drop is going up, and again, you can have just changes in the selectivity. Basically, how can you realize, I can understand something is going wrong, that you have fouling? Normally, when you have a transmembrane flux as function of time, if you don't have any problem with your membranes, you can have just if you're just working with pure water flux, normally at constant applied pressure, you will have a constant behavior of your transmembrane flux. When you start to work with a solution, so some solutes present in the feed can accumulate, can interact, etc., you can have a phenomenon that we studied already that we call concentration polarization phenomena. You can have the growing in some concentration profile in the solution, with the consequence that you are increasing the concentration at the membrane solution interface, and that means you can, if you don't avoid this increasing concentration and you work with constant applied pressure, you can decrease the effective driving force, delta P minus delta pi, and so you can have this kind of a phenomenon, a little bit decline in the transmembrane flux. But after some time, as you learn already looking from the equation, you can arrive to a kind of steady state. So nothing happens anymore. And this problem also is quite reversible. If you stop transmembrane flux, this flux will go up again. You just clean, you change the concentration profile. What can happen, however, so when you have this kind of phenomena, is just concentration polarization. when you have some behavior of this kind, you just go down, this part is the same, but you don't arrive to a steady state. You go on again for a long time, and asymptotically, you can go to flux equal 0, basically. Sometimes it takes a few hours, sometimes it takes days, sometimes longer than this, but that is kind of behavior. This is what we call membrane fouling, a constant, continuous decay of the transmembrane flux, and the consequence also in the selectivity of your membranes. This kind of phenomena can affect not only the behavior of your membranes at the moment, but lifetime of your membranes. Normally, when you install membranes in reverse osmosis, in ultrafiltration, in membrane distillation, you expect this membrane working for years, months, years, long time, as much as possible. This kind of fouling can just kill your membrane significantly. Lifetime, instead of being years, can become months or weeks, because this kind of deposit on your membrane surface can induce chemical transformation, pH changes, etc., etc. So we have to take care of the kind of phenomena. Now, which are the origin of the fouling? We were mentioned before adsorption, deposition, etc. A little bit more in detail, you can have the adsorption of macromolecular and colloid matter. Colloid matter are the most troublemakers. So when you have colloid in your solution, alumina, silica, or other species, that is a problem because you can easily form a gel, and this gel can just increase the thickness of your membrane. You can have the growth of biofilms on the membrane surface. We have two kinds of fouling, really. One is just fouling. And today, if you don't make mistakes, if you understand what you are doing, fouling is no more a problem. We have a lot of plants running where the fouling is under control. So we are not too much worried about fouling. The real problem today, in which still a lot of research is in progress, and we have really to make progress to understand, is biofouling. Biofouling is a little bit more complicated. Normally it appears after a long time. It does not appear in a few days or hours. It appears after 6 months or 1 year. And we will understand why. Because biofouling is fouling related to the formation of biofilms, and these biofilms takes time to be formed, and the real effect is not the presence of some biofilms, it's the presence of the products of biofilms. This means these microorganisms that form initially the film, they start to produce mucopolysaccharides, some chemicals, and these are the ones that can penetrate in the microporous structure of the membranes, of the nanopore of your membranes, and very difficult to be removed when they are already there. So biofouling is the real problem we have today, but normally biofouling will have an effect on long period, not in short time. Precipitation of inorganic matter, due concentration polarization, we can increase the concentration of the interface, we can arrive to saturation. Aging, the membrane itself has a problem of lifetime. Fouling can just induce some problem on the morphology, on the configuration of your membranes, and the aging of the lifetime of the membranes can be changed. Which are the major effects, factors that will affect the behavior of your membrane and the control of the fouling. Basically, the physicochemical properties of your membranes can be important. Hydrophobic, hydrophilic behaviors can have an effect on the overall fouling problems. The electrostatic charge, the fact the membrane is charged positive or negative, can have an effect. The function, the existence of some functional groups on your membrane surface can have an effect. In positive or in negative, we will see there is some way to control fouling just to protect membrane surface with some functional groups able to create a system in which, for example, adsorption is not very effective and so on. Physicochemical property of the solute, that means chemical property and physical molecular weight, hydrophobicity, again charge, size of the species is also very important. We will see that for some molecules, biomolecules particularly, the ionic strength of the solution And we will see, do you remember, ionic strength means the charge, the product of the concentration, mole per liter of your solutes, multiplied for the square of the charge of the ions forming your species. That ionic is very important because changing the ionic strength, you change sometimes this space configuration. Some protein, they can be linear at a certain ionic strength. They can be globular. Very different behavior for the same protein at the same concentration when the ionic strength is different. When you have a linear molecules and you have a globular molecule, the packaging of this kind of system can be quite different as for the final fouling behavior. Pore size, shape of the pore, just the fact that your pore has some tortuosity or just linear, etc., can have significant importance. All the operating parameters, transmembrane pressure, temperature, the flow dynamic, that means the cross flow on your membrane, that means the control of concentration polarization, which is related to this parameter, and properties of the solution you are treating. Concentration, pH, ionic strength, as I was mentioning before, and again, the history of the membranes. The membranes, in fact, is a virgin one, just used for the first time. A membrane that you have been using for months, years, and after washing, you use again, etc. The membrane is very difficult that you restore completely initial behavior, which means that the history can have an effect on all these other parameters. So you have to take care also of the history of your membranes. As you can see, many parameters can affect, can induce, can produce, can make more or less significant defouling, and that is making the story different. People have been trying more and more, and are still trying. In this country, you have strong groups here in Seoul, at the National Seoul University, for example, just working on the fouling on some membrane operation. There is one area, which is the membrane bioreactors, that is very important today, and membrane bioreactors are working on the municipal water treatment or in some quite polluted industrial waste, and the problem of fouling is significant. And they invented a way to reduce the fouling just in MBR, or to try to minimize this kind of fouling and to understand but the fundamentals of. If you want to start to understand about the mechanism of the system, you can already divide easily in what is called external fouling and internal fouling. We can have fouling on the membrane surface, basically. That means just, for example, forming a gel, increasing thickness, or fouling inside the pore forming your membranes. That is particularly true when you're working microfiltration, ultrafiltration, etc., a little bit less for the internal fouling when you're working with dense skin membranes. Reverse osmosis, gas separation are less affected by internal fouling for a simple reason that we assume that we don't have a big pore. But in all the other cases, we can have this kind of situation. For external fouling, that is one of the consequences. Number one, increasing thickness. And remember, transmembrane flux is reverse to the thickness of your membrane. You can have just, if there is a pore, you can have blockage of the pore. Just single pore can be just blocked. Or you can have a reduction of the pore diameter, of the pore size, by constriction of the pore entrance. Same is true for the internal fouling. You can have the internal blockage of the pore, just in the internal part, or some reduction of the diameter of the just constriction in your system. Just to mention what we are talking here is the external fouling, when you just have a deposition and formation of layers on the membrane surface, and here, where it is just the internal one, you can have just the situation in which your particles of the small size can just penetrate, and particularly due to the tortuosity factor, to the fact that pores are not linear and not all equal in diameter, you can have a region in which is easier for some particle to be blocked, and creating some significant resistance to the permeation across the pore. So these are two extreme cases. The effect at the end is this one. When you make your experiment, you can have here just the permeate flux. Do we have one that works a little bit better? As function of time, as I was mentioning before, that is the initial flux decay that you measure in the first few minutes or short time, and this is part of this is basically related to the concentration polarization phenomena, which can be formed in few seconds or just in few minutes. So you quickly see this. But after this, instead of approaching a steady state, you still have a decline, and that is not concentration polarization. That is just fouling, and that you must be worried, because if you stop operation, if you are working in a concentration polarization region, you can restore most part of the transmembrane flux and selectivity. If you are working in this region here, and you will not restore, that will be irreversible problem. Thank you. If that is when you are working as a transmembrane flux in time, if you just, one of the effects that we were mentioning is that the transmembrane pressure is just changing significantly. If you want to work at constant transmembrane volume, that is the kind of phenomena that you will observe. The TMP is just increasing, the pressure drop. That's what you normally measure in your plant. You have always 2 manometers in your system, in the entrance and the exit of your module, and you will see this increasing of the pressure, and that is evidence something's happening in your system, so you have to take care. And by the way, let's anticipate. This you have to understand what is going on, because normally when this kind of thing happens, and you are the operator, and you have to produce a certain number of cubic meter of your permeate per day, and you are in an area you want to go home, if something is happening and the permeate flux is decreasing, you increase the pressure. You say, let me just increase the pressure, and I will arrive at the end of the day with my number of cubic meter to produce in permeate. That's just the opposite. If you do this, instead of reducing the problem, that means instead of increasing the transmembrane flux, you will realize that this will become worse. If you increase the pressure when you have fouling, you will increase the possibility to deposit the solutes on your membranes, and that will induce more fouling. So instead of increasing the pressure, if you want to solve the problem, you have to reduce the pressure and eventually increase the axial flow rate, just the flux flow rate on your membrane, this just linear velocity. But it's just against, if you don't know about, it's against your instinct. You are just trying to increase the pressure and having more permeate for a few seconds, but after you will just make it worse, not better. What happened here? Sorry. Okay. Again, we can subdivide our fouling problem in different kind of aspects. We can have a fouling which is reversible, something similar to the concentration polarization phenomena. So after, when you realize there is some fouling, you can find a way to remove from the membrane surface using some physical methods, just by increasing axial flow rate or some other way of doing. But you can have also some irreversible fouling, cannot be easily removed by changing, for example, putting some more fresh water inside, etc. And you have to introduce some chemical cleaning, which is not nice, because normally with membranes we don't want to use chemicals. We want to reduce. We call membranes operation green technology, just because you don't induce some other waste coming from, for example, the chemical for cleaning. So we don't like this irreversible fouling. We like to operate always in situations in which physical cleaning is possible, as much as possible. What is worse, that there are also situations in which is not only irreversible, and you have to induce some chemical cleaning, but is also we will never be recovered. In some case, you can just change the membrane's properties forever. And that is something that also by cleaning, you cannot do anything. You have to take your module, your membrane, and put in the garbage. And you lose about 30%, 25% of your capital investment. Membrane have a cost. So when you have been creating some fouling, irreversible and not easy to clean, also with using chemical approach, this is a problem. Again, people have been trying to understand what is going on and assuming that we have this kind of different situation possible, where you have a complete blocking of your membranes by big particles that each one stop one of the pore, but there is no layer that can be formed. That is one situation. Another situation where you can block something, but in the meantime you form different layers of your particles. The situation in which you can just block not just on the surface, but inside the pore, and situation in which you just form different layers on the membrane surface. Normally, this kind of system has been utilized and they work when you are working in a dead-end filtration, traditional filtration, not membrane filtration. If you want to read this different kind of mechanism, you can go to years already in the 80s, and the expert in traditional filtration were trying to analyze this different kind of blocking that is normally in any kind of traditional filtration system. And they also wrote down an equation, and you can see here that this equation is related to this exponent n, and through phenomenological evaluation and assuming that just dead flow filtration, you can have that when it's just cake filtration, means formation of the layers on the surface, you have n is equal 0, intermediate blocking is equal 1, standard blocking 3 on 2, and 2 complete blocking, and for complete blocking is just 2. But that is something that as people have tried to extrapolate this kind of mechanism to membrane system where we don't have a dead flow. We always have cross flow on the membranes. So we have just trying to change this typical situation, and this kind of equation are not really very useful in the situation in which we are working with membrane system. Normally we have always this progressive pore blockage, and that we have this transmembrane pressure increase I was mentioning. You can also realize similar kind of phenomena, but at the end cannot be analyzed in the simple, relatively simple way that for standard filtration. So it's difficult to have this kind of nice situation, in which in this case you have just big particles blocking each one of the pore on your membrane surface. Normally the reality, you have a system in which you also small particles can just start to have some restriction in the transmembrane flux against single pore, also if they're not big particles, and the other particle present will form layer on this one. So the situation is a little bit complicated. To try to elaborate some equation, giving you the opportunity to predict the behavior, the resisting in series model with different kind of modification has been introduced. And this is coming, this one is valid for the membrane operation in general. And the number of resistance that are present in the system is related to your capability to describe all the phenomena that take place at the interface. So you can just assume a system in which you have, assuming always that you have a porous membranes and you are working at a constant pressure, you can assume that you have some polarization phenomena and some fouling phenomena. The overall resistance will be given by the total resistance will be given by the intrinsic resistance of the membrane, clean membrane, you can measure this value when working with water, and some other resistance, for example, the fouling resistance they are going to create, and the membrane resistance, as I was mentioning, as the intrinsic one. In this case, you can also assume that you can try to subdivide your fouling, your process in the fouling creation through a step in which you are forming a cake, that means a deposit on the membrane surface, an additional resistance related to the fact that there are some suspended solid present in the solution, particles, and this one just going to form this cake layer, or adsorption of the different species, colloid, soluble matters on the membrane surface, depending also from the chemical properties of your membrane surface. This term here can be obtained when you are working is clean water and there is no fouling, there is no deposit, no interaction, and the total resistance you measure at the end when the fouling has been created, and making a difference between the total and the intrinsic one that you measure initially, you can evaluate in the first approximation this RF. That means the resistance related to the fouling. And that is a relatively easy way of doing. However, there is a lot, it's not so easy in real life because there is always a different kind of interaction. It's not easy to separate completely the cake formation by the absorption, etc., because the interaction between the different kind of phenomena is significantly present, and there is a lot of hysteresis and not a synergic effect that you in principle have to consider. If you want, however, to try to use this kind of model, you can have the analogy with electric circuit, where you have all the different resistance that you are able to describe, and that means the total resistance that will be on the denominator of this equation. This is the transmembrane flux, is proportional to the driving force, that's typical Darcy law, and these are the terms that you can consider, where this RC will be the cake resistance, obviously this is the viscosity, the Rm is the total membrane resistance, and that is the term Rg is the layer that you have been forming, for example, a gel. If a gel has been formed, you are increasing the thickness with the gel here, and you have this resistance related just to the gel, and some resistance related to the partial blocking of your pore. So if you find a way to measure independently some of these, at least the three of them, you can have also the fourth one, but that is one way of doing, and people have been trying to do this. As you can see here, you can also try to have a more detailed analysis, and Korean researchers have been working recently and are still working in trying to analyze in some detail this kind of phenomena, introducing, you see, this is overall membrane resistance that you measure with using just simple water, and you have resistance caused by adsorption of some chemicals that are present. You have the resistance related to the concentration polarization. You have some resistance related to the reversible fouling resistance for some species that can be attached on the surface but can be easily removed. Reversible fouling we were mentioning before, and you can just increase linear velocity on the membrane surface, and you can increase in the shear force, and that can be eliminated. Or you can use what is today very usual, backwashing. At one point, when the flux is going too much down, you start to reverse the direction of the flux. Instead of having the driving force normal to the membrane surface, you just introduce a driving force from the bottom side up. So you just try to remove everything that was inside. So you just have this backwashing, which is now part of a lot of membrane. It's very important when you do these kind of things to know a lot about membrane morphology, because when you make the fact is porous, large pore, thin pore can have an effect on the prediction and the control of this kind of phenomena. And there is another term, which is irreversible fouling, that is not easy to remove by changing the shear force, but is strong interaction with membranes, and you can have again everything that is related, not external, but internal to the pore, with changing strong the shear force and just steering, etc., will have no effect in the pore blocking. When the particles are inside the pore, small particles that have been absorbed on the wall of the pore, not on the surface, this is a problem. It's a problem because also if you increase, you go to Reynolds 30,000, linear velocity 5 meters per second, the mass transfer coefficients of the particle inside the pore will be zero. They will not be very easy to remove them. So this is what we have to avoid, to the point that asymmetric membranes are quite interesting, not only because you have a very thin layer, and so you can have higher flux. But also because if you have a thin, dense layer of the membranes, or relatively dense, the number of particles that can penetrate is very low. So you minimize the problem of internal fouling. And that is one of the major benefits today in preparing some asymmetric membranes for controlling, at the best, the irreversible fouling related to the penetration on particle inside the pore. So that's one of the other. I would mention here that if you want, again, your Professor Choi, if he was trying to having some very good PhD student, try to fractionate all the different kind of fouling you can have, the irreversible one, the one related to the absorption, the one related to the membrane itself, etc. And if you can elaborate with, we have a new membrane where the only thing that you know is the intrinsic membrane resistance. After you can start to elaborate some tests, one by one, in which you can induce irreversible fouling by penetration of some particle that can go inside the pore, block, and never go out. And some other one in just by formation of interfacial layer and so on. So we just try to subdivide all the different kind of mechanism to form independently each one of these fouling and to find a way how to reduce them by flushing, by axial flow rate, etc. So this is very systematic and complicated kind of work. Does not solve the problem, but can give you some information. One more problem, quite important, significant, that initially was not considered, is the fact that in the previous model, we are just considering resistance related to some physical parameters, just to the fact that we can reduce pore size, increase the membrane thickness. But there is some more effect that people were not considering. When you start to work with microfiltration, ultrafiltration in general, you are assuming that the osmotic phenomena are negligible. And you have big membranes with a big pore, 0.2 microns or 0.01, etc. You are assuming there is no phenomena related to the buildup of polarization phenomena, concentration, polarization, and so on. This is not true. What you have to consider in your system is that when you have the formation of some additional resistance on the membrane surface, and that we call resistance related to defouling, this resistance can also induce some osmotic phenomena, because the additional membranes you are forming on the surface can reduce the behavior of your system from ultrafiltration, microfiltration to, for example, nanofiltration. These can be membranes with nanofiltration behavior, in which also some solutes of relatively molecular weight will not go through the membranes. They will accumulate at the interface, and they will create a concentration that will give some osmotic pressure significant. So initially, with the clean membranes, no problem, no osmotic phenomena. With the foul membranes, you have to consider the possibility of osmotic phenomena. That means the driving force is no more delta P, but is delta P minus delta pi. And that is one of the effects that people have been neglecting for a long time, and you have to consider. Also because you normally, when you are working ultrafiltration on microfiltration with high molecular weight particles, the osmotic effect is relatively small, because the osmotic effect is related to the concentration in mole per liter. So if you have very high molecular weight, the osmotic phenomenon is relatively low, Van 't Hoff equation. However, what is happening here is that if you concentrate the membrane solution at very high level, particles as amino acid, the sugars, or also some, not protein, but also if they have significant molecular weight, you can induce osmotic phenomena at the interface, where it's important, because what happens in the bulk, we don't take care, but the interface is important. So we can have osmotic phenomena much more often than expected. So this is one of the things we have to consider. And so that's why we can have this model where we not only introduce fouling resistance, different form of fouling resistance, but also the osmotic effect. And that's why that is one of the points that is important, because very often the people were assuming that there was no osmotic effect. And all the problem was related to the formation of eventually this bulk layer. But when you form this fouling layer, a cake or a deposit or a gel, what it is, this layer is not only an increasing of the thickness, but can be also induce a change of the interfacial concentration, and so can induce osmotic phenomena. So you have to take care not only of the simple increasing of the thickness, but also of the phenomena induced by the formation of this layer, which can affect the concentration profile at the interface. And that is the one correction that today is becoming relatively normal. Now, in the past, people were just making mistakes, because they were assuming that just for increasing the transmembrane flux, they had to reduce just the thickness. It was not the case, because part of the problem they had was not related to the thickness, but was related to the different concentration of the interface, to the osmotic effect that are present. And here is a typical case to confirm this kind of observation. That means that when you change ionic strength, as I was mentioning before, we will see what it is, and you have a membrane which has no charge, very low on the surface, and the membrane which has a negative charge, cationic membrane, etc., and you can have different behaviors when you are going to compare this negatively charged and the neutral in exactly the same membrane, same concentration, same time, and you can change the story of the system. That's why the ionic strength is very important. Just to remember, ionic strength is this kind of definition. Ionic strength is nothing more than the concentration of all your ions, if you sum, you add all of them in your solution, multiplied for the square of the charge. It's not just the concentration which is affecting this kind of interaction, but it's just the concentration multiplied for the square of the charge. This is a very important parameter because, by the way, this is the kind of parameter that is at the origin of definition of activity coefficient. If you want to understand why, when you are increasing the concentration of the ions, you have a deviation for the theoretical behavior, for ideal behavior solution, is related to this kind of phenomena. What is called the Debye-Uchel theory, when you have this, because these ions are not existing by themselves, they have always have a Debye cloud around. That means there is different other ions that form a kind of sphere around the single central positive or negative ions, and this Debye-Uchel theory will predict how the behavior of these ions in this system related to all these electrostatic phenomena are changing the behavior of the solution, increasing concentration, so you have deviation for the ideal behavior when single particles are present due to this system, and these clouds are very sensitive to this kind of term. So this has been introduced on the basis of the Debye-Uchel theory. That is one of them, don't forget, because that is the one that you have to consider when you want to understand what is going on in your solution. Is the question of not only of the concentration of your ions, but the multiplied for the square of the charge. That means double, bivalent, trivalent can have an effect much more significant than monovalent and so on. You can find definition in molar or molality. That means the different, just molality is grams per liter instead of mole per liter. Anyway, and the same effect here. For example, when you are working with adding some calcium concentration, and you can again working with some negative membranes or neutral membranes, you see you can have a significant change in the transmembrane flux behavior just by adding some ions that you assume are going through. Calcium ion, people say, why do we have to expect change in transmembrane flux? This is ultrafiltration experiments, big pore, that only protein or big molecule will be blocked, eventually creating layers, etc. If I put some calcium are small molecules, are supposed to go through the membranes with no effect on the transmembrane flux. It's not the case. It's not the case because calcium ion can change ionic strengths, and ionic strengths of the system can change the absorption, the interaction, the configuration of your particle in the solution, and that is the final result that you can have just adding some small molecules permeable across the membranes. Due to the change in ionic strength, you change the behavior of your system. So that's you have to understand. For trying to understand the story, people try to identify how the mechanism of some absorption. Absorption, as we discussed, is number one. When you want to make some study in this area, you normally start to use the humic acid in brackish water, seawater desalination or purification. Humic acid is always present in any kind of water, is assumed to be one of the typical example, and you can try to identify the mechanism in which this humic acid interacting with some cations will form some layers, will be absorbed on the membrane surface. And again, here there is, you can have what is they are called some very weak interaction, some strong interaction. You can have a state in which we are forming these kind of molecules in some state where you arrive to a steady state. Just to show you that people have been trying to understand what is going on just because this phenomenon is present in any operation. We discussed already this kind of results. What is happening in your system is at one point the transmembrane flux that initially with water was nice and linear. Now we understand that you can have this kind of a behavior. So something starts to deviate from the water, but at one point not only deviate but become constant, increasing the pressure. What is going on here? And we learned already that is what we call a gel model. When you form a gel layer at the interface where the concentration is becoming constant, that is the situation that you create. You have a balance of back diffusion and convection, and at the interface constant concentration. When you form the gel, don't change anymore, and that's what is happening. And that is a function of the concentration of the solutes. Here is a hemoglobin was 75%, 0.75, 75 10 to the minus 2, 75 10 to the minus 3, and you decrease in the concentration, this situation appears at very much higher transmembrane flux than when you have 2 order of magnitude higher. And the other way of changing, we already discussed it by changing, trying to destroy the phenomenon of the interface by increasing can be the steering or increasing the axial flow rate, and you can again have this kind of phenomena. Remember, to avoid this, in all membrane operation, this is the way in which we operate. Dead flow is not part of the real membrane engineering. That's what the traditional old kind of filtration system, which people were discussing about annual 0, 1, 2, 3, what it is. We normally work in cross filtration, and the system is quite different. That is the one you just want to see if it's real, that your membranes is just changing with time. You can just have a look and make the analysis of the membranes in presence or not of some transmembrane flux decay, and you can really visualize how the surface of your membranes is changing for the deposition of something on the top. And that's something that can make clear the situation. Something about biofouling. Biofouling, I told you today, fouling, if you're not able to control fouling, you are not a good membrane engineer. In any situation, with protein, with antibiotics, with salts, with amino acid, you must be able eventually to some pilot testing, some experiments, to identify the level of irreversible fouling, to operate in situations in which you don't induce too much fouling, etc., etc. This same story is not true for biofouling. And the reason is that still we don't know in detail the origin of biofouling. That means which are the particles, which are the microorganisms that are inducing biofouling. And how they grow, why they grow, and how they grow. It's not easy to anticipate, and there are a lot of people here, again in Korea, studying. For example, a very simple approach, but quite interesting, is that the origin of this biofouling is the formation of biofilm. By the way, biofilm is a very general problem. We have biofilm in our body, and we have biofilms in many other situations. So biofilm is a very interesting area of research. they are trying to understand, for making a film, starting from 1 or 2 microorganisms, from one bacteria, etc., these microorganisms, they are alive and they communicate. They have to be able to interact and to grow and to produce something. So one approach is to find a way to stop communication. If you invent how to avoid communication between different particles that have to communicate, that can be one of the approach to minimize the formation of the film. So to keep always single particle by themselves. Because when they are 1 or 2, that's the problem with biofouling. When you have your macroporous membranes, on the membrane surface you have some pore, on one of these small particles are going through with no problem. There is no, eventually, if you are not able, there is some fouling, but you have to increase the axial flow rate, you make backflashing, everything's okay. When you have 1 or 2 big particles that are just absorbed on the membrane surface, you don't realize there's no problem. Only 1 or 2 big particles, osmotic effect, 0. Too big, so very, very low osmotic phenomena. Change in thickness, no change in thickness, because it's single particles. So no real problem. The real problem is when these particles, if they have some nutrients around, they start to grow, to interact each other, and to form some homogeneous film, and eventually they penetrate in the pore. And when they penetrate in the pore, no way to remove them. These things takes time. So you realize at one point that everything was okay, you have very slow decay, but say not very significant, but and when it starts to be significant, when the film is formed, too late to clean the membranes, and you lose all your system. And that can be a very severe. You have to stop the plant and change 100% your membrane sometimes. That's why we have to, there is a lot of work going on in this area, and trying to understand which are the particles more dangerous and how they communicate each other for creating this kind of situation where you start in this, you see all this interconnection, and that is the real problem. That is the particle that we have to control, the external polymeric substance. That the trouble is when this kind of particle, they start to produce by themselves. They are starting to produce themselves the microorganisms. Because the membranes is a very nice nutrient, by the way, and the environment can be a strong nutrient. So that is what is happening. And also if 90% of what they are forming here, this biofilm is still water, but they form homogeneous film, and that is what is creating the real trouble in this situation. And again, people, as you can see here, just also a Korean researcher, are just trying to understand how these 1 or 2 single microorganisms are related to this external extracellular polymeric substance that can be present, what they form, and how they just create some particles, some clusters that eventually interact with the membrane surface and create, through the accumulation, they start to create a real problem. And the real problem, when they are able to penetrate and to form something inside. There is very loosely bound EPS, there is a much more strongly bound EPS, and that's we start to understand a little bit what is going on. And you can see physically, by sophisticated microscopy, etc., how these things grow and how they are interconnected. These are the origin of this biofouling system. Now, the problem is that when you are in real life, and you see here is day, some situation is of this kind, that you can, when some kind of bad fouling phenomena take place, and particularly the one also with bio, you can have a situation in which with time you have this kind of behavior, and that is not a big trouble. In some case you can observe that you start to deviate, the pressure drop is increasing, but you have also a situation of this kind, where suddenly when you are working with, in bad case, with high transmembrane flux also, the transmembrane pressure is going up and you have to stop the plant. You can block everything. The driving force is becoming not sufficient for solving any problem. And also here, people are trying to understand what is going on, and the fouling mechanism, the overall fouling mechanism, working with constant flux has been subdivided, as you can see here, in what is called a conditioning fouling, initial step of the problem, where something is starting to happen, initial pore blocking, and finally we have, you arrive at a kind of a steady state, a steady fouling, traditional one, but if you are not able to control what is going on, suddenly you are in this kind of situation when this transmembrane flux is becoming jump up, and that is a problem. And that normally happens when you are overcoming critical flux of your system, and you have this kind of situation. And you can again visualize this, and that's the problem. You can, when you have this formation, just covered on the surface, you can have this kind of situation. This one can be physically clean. It's relatively easy to remove this kind of deposit. And you can have a situation a little bit more negative when you have some cluster of bacteria, this green stuff, that means something is growing, but the worst when you have this situation. When something with this bacteria, they start to penetrate in the membrane porosity, in this case, you just probably, what you have to do is to put your module out and buy a new one. There is no way to solve this problem. That's why you have to invent system for to avoid this kind of problem, which is not easy, by the way. When we are talking about this, you don't have a real concentration of microorganisms. You have parts per trillions, 1, 2, 3, that initially start to grow, but after they, with the nutrients which are in the solution, they grow and they can create the real problem. This problem is very important, I was mentioning before, in the submerged membrane bioreactors. You know, this, how to control the formation of fouling on the membrane surface is very, very important, because we are going to grow thousands of these kind of units all around the world, all around your houses, in the condominium, etc., and treating very bad wastewater. By definition, when you are working in membrane bioreactors in the submerged configuration, that means you are putting your membrane, this is the biological tank where you are just discharging all your waste. Inside you put your ultrafiltration membranes, and that operates in a different way than normal. You make a vacuum inside so that the clean water will penetrate here and you extract clean water. That's what is going in this MBR. By definition, here you can have a lot of pollution and a lot of fouling, because there is a high concentration of bioparticles or microorganisms, etc., etc. So how to clean is very important. You can have different kinds. Sorry, what is it? So destroy it. What is important here is just the evolution of the permeate flux. We show already this kind of diagram. You can have a situation which you have just your, you have this transmembrane flux as function of the transmembrane pressure. And you remember that we were defining a critical flux, this one. When you're just increasing the transmembrane pressure and you stay with a linear relationship, you are working the right way. That means that if you want to go back here, everything is reversible. After this critical flux, you start to have some this kind of behavior related to the fouling, which is not reversible anymore. If you stop here, when you go back, you have a hysteresis here. So you have a deviation. So you cannot restore the initial flux. And that's the situation we want to avoid, because this situation can create more and more problem, and this kind of reversibility is becoming worse and worse. You know, the next step, if you go up here now, you have this one going down here and down here, so you really foul the system. And that is what we have to avoid. I was mentioning in the previous slide that the way for doing this, there are different. You can have, for example, you can see here aeration. And is one way to minimize also this fouling. You're just trying to have a continuous bubbling air going in and trying to minimize the absorption of the microorganisms on the membrane surface. So this is one of the, or you have to clean the membranes and find a way to avoid all these kind of things. And this critical flux that we mentioned is quite important. And if you go a little bit more in detail, there are people who have been working on this, and you can have what is called a strong form of critical flux and a weak form of critical flux. So this is the strong form is the one in which the transmembrane pressure starts to deviate from the linear pure water line. That means this is the situation that you have in step number 1, and you just start to deviate from here, you have this kind of irreversibility. But there is another one, and that is called the strong one. When you have a weak form, that means you start immediately. When you start to grow in the flux with transmembrane pressure, deviation is immediate. And that is the worst situation, because that is for sure, you will never have a linear behavior here. And easily you will arrive to what is called also this situation of critical limit. And again, you can, using the same equation we were discussing before, you can try to identify this kind of relationship between flux and the different kind of resistance, assuming that there is irreversible resistance or reversible plus the resistance of your membranes. And you can see here that we can define a critical flux in a situation in a strong form in which the fouling condition are the one really controlling the problem. And in this case, we immediately have the deviation from linearity, and we assume that osmotic phenomena are not present. This is a wrong assumption. Very often is not always valid. And, but you must have at least one significant irreversible kind of fouling present. Now, normally in this kind of relationship, we are assuming that the adsorption is not significant, the reversible is not very important, the osmotic phenomena are not significant, but the irreversible, when you start to a deviation, is significant. And you can have situation different in the weak, in which you are assuming that the adsorption is significant, that the osmotic again is not significant, the reversible fouling is not significant, but adsorption and irreversible are significant. And that means adsorption is taking place immediately. As soon as you start to operate, you have deviation from here. So you can have a different kind of relationship between resistance, driving force, and transmembrane flux with these two kind of situation. And this irreversible critical flux is the term that you have to try to understand as soon as possible when you start your operation, because that is the one that is really controlling both the weak and the strong transmembrane flux in your situation. And people have been also trying to develop different methodologies for measuring the critical flux. The easiest one is just to measure the flux and pressure profile and just to detect where this deviation from a linearity is a relatively simple method. And the only thing that is very much related to your capability to make the measurement clean, to be sure that you're not making mistakes and good reproducibility, etc., etc. And this particularly is used particularly when you are working with relatively low concentration with no osmotic. The approximation of neglecting any osmotic phenomena is valid. Otherwise, the system is not the most appropriate one. Okay. Remember that we defined already also limiting flux. The limiting flux has nothing is not the critical flux. Limiting flux is this one. And when you approach the limiting flux, no further increase in transmembrane pressure is effective. You can increase the pressure, the flux will be constant, will go always here. And that means the limiting flux is the flux that corresponds to the situation which fouling saturates the filtration capacity of the membranes. In a situation in which you can double the pressure, the driving force, flux does not change. So the fouling phenomenon that you have been creating, formation, for example, of gel layer, has completely blocked the possibility to improve the performance of your system. There are some parameters that you have to remember that you will find very often defining the property of your system. So how I can predict if my membranes are appropriate or not for working with my in the operation, as function the possibility to have fouling. And that's particularly for seawater, brackish water. So one of the parameters that has been identified that everybody has been using until recently, which is not really accurate, in fact you will see we already has been modified, is what is called silt density index. And this is a standard methodology, and you have to compare results to identify the performance of your membranes in front of some separation you're looking for. You have to follow the rules. This silt density index is the capacity of the water to foul the membranes following this kind of determination. You have to use a 0.45 micron filter at a pressure of 207 kilopascal, 30 psi, all very well standardized, room temperature, 25 degrees centigrade, and this is an ISTM standard method. You find in the encyclopedia on the books. It's ISTM 2007, that is the one in which has been published, and is a D4189. The equation that you are using in this case is this one. SDI is 1 minus T1 on T2 over T per 100, where T is the total time, elapsed time, and T1 and T2 are the times measured in seconds required to filter through these membranes, 0.45 microns, 500 milliliter of water, initially and after T minus respectively. That means you start with clean water. After 500 seconds, you measure again, and you have different time necessary for filtering these 500 milliliters. And on the basis of this, that is the time, the total time that you have to decide is normally defined as standard, 15 minutes. Okay? So this is the way to tell if your membranes of the solution can go through your membranes or not for avoiding fouling problem. Normally, this number has to be supposed to be between minus then 1 is some good number, 1 or 2 is a good SDI for treating with reverse osmosis membranes in a spiral valves, etc., seawater. If you are going to 6 or 5, forget. This water has to be pre-treated, otherwise you will have a big fouling very quickly. If you are of the order of low than 1 or approaching 1, sometimes also 1.5, 2, you can operate without big other treatment. You don't expect a big fouling. This kind of standard methodology has been used until recently. Today, people realize that this is not the case. First of all, when you make this filtration, is again cross flow, is dead flow, is not cross flow. All our systems normally are working cross flow. Second, we are learning that the particles at the origin of the problem can be much smaller than the one going across 0.45 microns membranes. People were assuming that the origin of the fouling was mainly related to particles of a certain size, protein, polysaccharide, etc. Is not. Today, the microorganisms, particularly forming the first bacteria, etc., can be particles totally different, very small molecular weight. So there is now a modified fouling index in which particularly the time for the transferring all the solution across is no more 15 minutes and is recorded as 30 seconds. And the situation is that in this case, the first one, the MFI is calculated as standard reference of 2 bars instead than before was, I think, I don't know if you remember, 15 temperature was 20 degrees centigrade. The surface area, here they are still using 45 micron membrane, is larger than the one we have mentioned before. However, this one has been defined as a modified fouling index, basically because they change the time in which you measure your volume. But this is not the most important one. Well, here, as I was mentioned before, this, about 3 is still good for RO. In some cases, you can go also a little bit higher than this, but more than this, you will have, by definition, big filtration. The modified salt index have some advantages. First of all, I was mentioning there is the situation that is not just, let's see where is this one, there are still 0.45 microns. The most interesting one, remember only this one, is the one in which you have this MFI, where instead of using 045, which is basically microfiltration membrane, we are using MFI-UF. That means the membranes, the ultrafiltration, which is able to stop also particles much lower in size than the one that the 045 can measure. And that is the most up-to-date standard methods that many people still don't want to use because it's too severe to control the real control of the fouling. And the system is relatively easy, and everybody has to use the same kind of system. You don't have any flexibility in changing the system here. In general, how we can avoid all this problem? This problem can be avoided by having turbulence promoting the system. That means enhancing as much as possible this surface, just cross-flow filtration. We can have some, instead of using turbulence promoter, we can have corrugated membrane surface. You can have membranes with some profile inside. That's another way to induce Coriolis acceleration. You can try to detach. You can have flow that is just pulsing. You can have vortex generation. You can invent how to induce vortex in the system. You can have this two-phase flow. Eventually, you can have bubbling of air inside. So different way of doing are present. The most interesting I was mentioned before is the backflashing. The backflashing is a method to reduce fouling by having this kind of situation. When you start to have deposition of something on the surface or eventually inside, what you have with some frequency in automatic is already, the apparatus is already well done, you can start to have a backflashing here. So this backflashing will remove the deposit and just avoid the growth of the deposit. This is the situation we are talking about. When you have, as a function of time, this was the transmembrane flux, was going down, and that without any backflashing. Now you start every, and that you have to learn by yourself, every seconds, every 10 seconds, every minutes, every 1 hour, you have a system which in automatic will reverse the flux, and you just work in this way. So if you are working this way, you can solve a part, you have the decay again, etc., but the average will be this line and not this one. So backflashing is one of the best ways, particularly when you're using microporous membranes or some ultrafiltration membrane. When you're using ceramic, for example, this kind of system is the one that today is more and more operate. And normally, you can have this kind of behavior. And that is just the standard. You can, instead of going down quickly, you can have a behavior of this kind. Just to mention that you can also minimize the kind of phenomena, as I mentioned before, by modifying the surface. We learned that the most part of the fouling is related to adsorption or to deposition, etc. Deposition we can solve by flow dynamics, basically. Adsorption we can also change by functionalizing our surface. For example, you can just graft the membrane surface with some amino acid, short chain, and this is a way to reduce protein adsorption. There are many of this kind of way of doing. You can just invent one by yourself, and basically this graft polymerization is one of the technology that people are using. By the way, most parts of the membranes at commercial level, keep in mind, are not the one you are preparing in the lab. Most parts of the membranes are always a coating on or some deposition by plasma, by just grafting, by other ways. So there is always something you have to use to protect as much as possible your membrane. The membranes is one of the significant costs of the system. If you want to summarize all this kind of effect, you will see here. In terms of just of hydrodynamics, no chemical effect, that is the situation. In the past, people know, if you just are working, this is, you put your permanent flux as a function of time, in dead-end filtration, that is the kind of behavior you have, significant flux decay and going down. Now, if you just try to solve this problem only by increasing a little bit axial velocity, you have some benefits, but not too much. If you look here, today, the best way for solve the problem is this one, which is the backflashing. The backflashing combined with air bubbling. That's what people we are using today in MBR. You have a backflashing with appropriate frequency. The frequency has to be done on a pilot plant, you have to learn. But if you combine Backflashing with the bubbling of the air, that means during the process you have a continuous air injected in the solution. That is the kind of behavior you have. You are working up here and not instead working down here. If you only use air bubbling by itself or backflashing by itself, backflash is really good, but air bubbling is down here. When you combine the two, this one with this one, you have benefits, and that's the best way that people are using today. And you can see here again just the combination of the two that you can see how the system, this is surface when you are using air bubbling and just a little bit higher axial flow rate, but that's the situation when you combine the two. Much better just also having a look. And that's the same presentation that today. That is the cleaning time necessary when you are working in dead end. A lot of time is necessary, you can see here, to make to clean again your membrane, enhance cross flow, air dispersion, but the backflashing and air is down here. So in a few minutes you can restore basically your membranes and you solve your problem. Just to mention, before closing, that until now we have been discussing of what we can call traditional form of fouling. Fouling that people have been studying for a long time on ultrafiltration, reverse osmosis, nanofiltration membranes. But today we are learning and we are studying new kind of fouling. Some of your colleagues today are studying not fouling related to this kind of chemical deposition, cake formation, etc., but they are looking to, for example, change of chemical properties. We will discuss in the next lectures about, for example, membrane distillation. In membrane distillation, most part of the traditional fouling is absent. We don't have any difference in pressure. We don't have high convective flux on the membrane surface, so there is no accumulation of chemical on the surface. But we can have some other different kind of fouling related to the possibility to change the properties of your membranes. Membrane distillation, we will learn, is very much related to the surface energy of our system and to the surface tension of the membranes you are using. For having membrane distillation, we will learn you need hydrophobic membranes, not hydrophilic. If the membranes from hydrophobic became hydrophilic, you block the system. Membrane distillation does not work anymore. We never discussed about this. Hydrophobic, hydrophilic in ultrafiltration, etc., can have some effect, but not very important. Here is strategic. So we have to control the wettability of our membranes, the possibility that you can interact with some chemicals present in the feed solution, alcohols, acetic acids, dimethylformamide, acetone, etc., and be sure that we don't change at different level of concentration, we don't change too much the surface tension of the system. If we change, that's what can happen. We can have situation, sorry, this is a different one really, but we can have a situation in which in this case, water entry pressure change very much. Here is changing for the size of the membrane pore, which is another effect that we have to consider. But you can have similar phenomena because the membranes is just changing going from hydrophobic to hydrophilic. And that's why we have to be sure that we can operate in this kind of situation. This kind of situation, flux and function of time, in when there is no fouling at all, and the membranes has the same properties in terms of hydrophobic, hydrophilic, and general fouling phenomenon. This kind of system today start to be possible. Years ago, they were not possible at all. But this one we will discuss, just mention that is a special form of fouling, not traditional at all, coming with a new process. For example, if you are working a solution with concentration of alcohol higher than 35%, all the membrane that people are using AMD lose hydrophobic character. And so you have to find a way to avoid this kind of situation. All this discussion has been done only on fouling and on what happened on the single module on the surface. Keep in mind that there's another big problem on how to control this kind of a problem, and it's not only working on the single module, but also the situation, the mode in which we develop and design, the overall process is very important. It's very important for increasing the productivity of your system, but also to control fouling phenomena in a different module that you are putting together in a big plant. Normally, this is a kind of batch system that is the easiest way for using your module, in which you have basically, that can be also with a steering system, etc., but it's a batch operation. Membranes have the possibility to operate not in batch. A lot of system, when you have a batch system, this is discontinuous process. You have a batch, 5 cubic meters of solution to be treated, you put in the system, you filter, eventually to minimize this formation of big fouling problem, you just steer the system, etc., but it's a batch. When it's finished, the 5 cubic meter, you have to start again, and you put other 5. Membranes are always in cross flow, and membranes are quite interesting because you can move from batch system to continuous system, and that's very important. Fermentation, some big plants or production of emulsion, etc., can be redesigned as a continuous system, no more as batch system. And this is traditional way of doing, in which you just have your feed, and as you know, we can have at the end, we apply a driving force, we have something going through and something that will the concentrate we can eventually recycle. But the recycle of this concentrate can be done in a different way. You can just discharge, single step, so something's entering, and after you have a filtrate and a retentate. In some cases, what you can have your filtrate, but you can recycle the retentate back in the feed. And so the system is going to produce more and more up to a certain level. Here you can just induce what is called diafiltration that we mentioned at the beginning. But we can have also more stages. You can work in a series. You can have stage 1, stage 2, stage 3, in which each one of the concentrate or permate, is up to you, will become, assume this one is a permate, is a concentrate. This concentrate can go together with the other one as a retentate, but we can also just have in the same line the concentrate from stage 2, the concentrate from stage 3. So at the end you have 3 steps in series, a filtrate and 1 retentate. Or we can have a cascade. You can have in parallel 3 modules, 2 modules, 1 module. Again, you can collect all the retentate and all the filtrate. And these are only some of the possible configuration, and you can have much more than this. And the motivation for doing this is on one side to control the overall capacity, not related to one single module, but the other one is to control the capacity, reproducing for a single module the same performance that will be present in all the other one. Not easy. If you don't do this, you can have a nice, clean transmembrane flux here and big fouling here on here. If your retentate is too high, the recovery factor is too high somewhere, and so you have to redesign the system, taking care not only of the overall productivity of the system, but also of the fouling phenomena that you are going to introduce in the single one. And these phenomena are always, again, present. Okay? Questions? We have been trying to run a little bit because we had to finish this part, otherwise we were late. But if you have any problem related to this, you will find everything in your note, but come and we will discuss a little bit. Okay? Questions? Okay? We meet on Wednesday. We will start next week to discuss some specific process, as the membrane distillation, for example, and gas separation, etc., before going to some application. Okay?